Now, after looking at the conformations of ethane and propane, let's finish by looking at conformations of butane. This is the next higher homolog, and the structure of butane is CH3, CH2, CH2, CH3. There are two different kinds of CC bonds in butane. There are these peripheral ones, and we could look at those, but their analysis will be fairly similar to the analysis of propane, because in reality, switch going from methyl group to an ethyl group is not that long, since we're switching in just one linear dimension, but the other two dimensions remain the same. However, we'll not look at that one. We'll instead look at the central bond, which will allow us to get some new insight by studying the conformation relationships of the two methyl groups and the torsional angles between the two methyl. And so let's just start by drawing out the different Newman projection formulas for different conformations of butane. So we'll start with an with the staggered conformation. And we'll abbreviate this as stag and label the structure as A. And then rotation about 60 degrees gets us to an eclipse conformation. Let's call this B. Another rotation takes us to another staggered conformation, which we shall call C. Then we go to D, which is eclipsed again. Another staggered conformation follows, and this one we shall label as E. And the final conformation is eclipsed again. And we'll call it F. Of course, the final rotation gets us back to the structure A. Now, so we have now three eclipsed and three staggered conformations, but the question is, are they all equal in energy? And if we look at them a little bit more carefully, some of them really are equal in energy. For example, conformations E and C are nothing else but mirror images of one another, so they're obviously going to be equal in energy. The same will apply to conformations F and B. And of course, any eclipsed conformation will be less stable than any of the staggered conformations. But things do get a little bit more complicated. So if you look at our conformation A, this was a staggered conformation, but two of the big groups, the methyl groups, are exactly opposite from each other. And this conformation is called anti, when two of the big groups are exactly opposite from each other. And this is the most stable conformation, because one can imagine that the bulk of the repulsion will come from the repulsion of the big groups as opposed to the small ones. And thus, putting them as far as possible from each other is very favorable. The conformations C and E, while both still staggered, have this relationship of CH3 groups, which is kind of unique. They're staggered, but their dihedral angle is 60 degrees, as opposed to the empty conformation with 80 degrees. And so, even though they're not eclipsing each other, they're still relatively close to each other, which brings in some instability. And this conformation is called gauche, which comes from the French word or meaning awkward, or left-handed. This is obviously a little bit of an old language when left-handed people were thought of as strange. And this is second most stable conformation. Now the eclipse conformations are also different. And the difference comes from the different energies which are associated with eclipsing two metal groups or eclipsing metal group with a hydrogen. So this would be the so-called totally eclipsed, which is the least stable, because two metal groups are eclipsing each other. As we've seen before in the case of propane, having a metal group eclipsing a hydrogen is actually not so bad, not as bad as you would think. So this would be just a normal eclipse, which is second least. Now with this data in hand, we can go ahead and construct the energy graph, which in the case of butane will be a little bit more complex than in the case of ethane. So if we again plot relative energies here and the theta angle here in degrees, we will start at a 0-degree angle, which will represent the totally eclipsed structure. Sorry, I should probably redraw this. So the total eclipse structure will look like this. I will just point out the metal groups for clarity. Moving down to the 60-degree angle, we will get to the gauche conformation, with two metal groups at a 60-degree angle from each other. Going a little bit higher, we get to the eclipsed conformation again, but now two metal groups are not eclipsing each other, instead eclipsing hydrogen, which we're not showing. This is 120. If we go further down, we'll reach at 180-degree angle the anti-conformation, the most stable one. Coming back up, things are symmetric, so we'll have another of the eclipsed ones, another of the gauche ones, and finally another of the totally eclipsed ones. And the corresponding angle will be 60, 120, 180, 240, 300, and 360. So what is transpiring here is this general shape of a curve where we go down and then a slight hill, and then further down. And here at this intermediate values we'll have the two gauche conformations, the two that are mirror images of one another, and at the bottom we'll have the most stable anti-conformation. If we look at these energy differences, the difference between anti and gauche conformation, this is an important number, is 0.9 kcals per mole. So you can see that the gauche conformation is quite unfavorable actually. The difference between totally eclipsed and anti-conformation is very large. It's about 5.0 kcals per mole. And finally, I'll plot this on this side to avoid confusion. The difference between the anti-conformation, just a normal eclipse conformation, is about 3.6 kcals per mole, which is an intermediate. From these values, all others can be extrapolated. So again, we see that this overall rule that we've established with ethane, that we go from staggered conformation, which is stable, to the eclipse conformation, which is unstable, still applies in butane, but the energies get to be a little bit more complex and slightly less regular. Now, this what is clearly striking is this 5 kilocalories difference, which is caused by the total eclipse conformation of two metal groups. And you can see there that since metal groups have all these hydrogen attached to them, bringing them to close contact with each other allows for a lot of clashing here. And this concept is known as steric strain or steric hindrance. And it's a very important concept in organic chemistry. We'll see this over and over again. Now, but the important thing to mention at this point is that 5 kilocalories per mole is really not that much energy. And many molecules, even at room temperature, have that or higher amount of energy available. And so what these molecules do is continually jump over these barriers. And so all of these conformations are populated by a certain number of molecules. It's just that populations of these different conformations are relative to their energies. So by saying that we have this eclipse conformation which is unstable, that doesn't mean that we will not have a single molecule which is an eclipse conformation. It just means that we'll have less in eclipse conformation than in staggered. Now, a molecule of butane, especially its anti-conformation, is a good model for higher alkanes. Because just like which have a lot of these internal CC bonds like butane. So just like butane wanted to get to this very stable anti-conformation, so will all the other alkanes, and furthermore, so will each and every CC bond in that other alkane. And so we will end up with is this anti-relationship around each CC bond in a higher alkane. So you can see that, let's go to the next one. So you can see that here that these two CC bonds are anti to each other, and each subsequent one will be the same. And so what we end up with is this zigzag conformation, which not only looks very symmetric irregular, but it is indeed the most stable one in higher alkanes. With this, we will finish today's lecture. It is quite challenging series of concepts, and for the first time it requires you to really think and analyze things in 3 dimensions, which can and probably will be difficult because we're still dealing with just the 2-dimensional projections of these dimensions. So it's important that you practice the conformational analysis on these systems and as well as on the more complex ones. Thank you.